Welcome to States of Matter at STP and Allotropes. You do need to be able to identify an element's state of matter that you would find it at its standard temperature and pressure. There are two ways to do this. You can do this based on reference table S if you're a looker-upper kind of person, or you can do this based on memorization if you're a memorizer kind of person. I don't care which one you use, so I'm going to show them both to you. Start with memorizing. If you're a memorizer, if you're sitting in my classroom and you look at the front of the room, my periodic table has these nicely coded. So as you kind of look at them throughout the year, you might actually already know some of these. The easiest thing to memorize first is that you have two liquids on the periodic table at STP. You have bromine and you have mercury. So those are your only two liquids at STP, bam, you're done. Gases at STP is a slightly longer list. Hydrogen, nitrogen, oxygen, fluorine, chlorine, and the noble gases. You're going to notice that there's some of the diatomics, but not all of them. The noble gases should be pretty obvious to you to be gases. And some of the other ones you already know, like you should know nitrogen's the primary component of our atmosphere. You're breathing oxygen right now, so some of these might be a little bit obvious to you, making them a little bit more easy to memorize. Everybody else is a solid at STP. So if you look at the rest of the periodic table, if you're looking again at the one in my room, you see those elements that are coded in black. It's the vast majority of elements on the periodic table. Those are your solids at STP. So you hate memorizing, do you? That's okay. There's a way you can look this up on table S. First, you have to know that standard temperature is 273 Kelvin. So you can find that again on reference table A. So we're basically talking about when we're at 0 degrees Celsius. The reason I put this in Kelvin is if you go to table S, your melting and boiling points are given in Kelvin. So we do need to compare 273 to where it's going to fall in comparison to these properties. So if 273 is below our melting point, we'll have a solid. So what I'm going to do is I'm going to look for where 273 falls. If it's below the melting point, solid. If 273 is between the melting and boiling point, we have a liquid. And if 273 is above the boiling point, that element's a gas at STP. So I'm going to start with hydrogen. Hydrogen's melting point is 14. Its boiling point is 20. 273 is above 20, I think. Just kidding. So that's going to be, that tells us that hydrogen is a gas at STP. I'll just write a little G there for a minute so we can kind of keep track of what we're doing. Helium, we got a melting point of 1, a boiling point of 4. Those are also low. Again, 273 is going to fall over here in this gaseous range. We would expect helium to be a gas at STP. Both of those agree with what I told you right here and what you would see if you looked at the coded periodic table in my room. Now for lithium, 273 is way down here below 454. So that tells me that I expect lithium to be a solid. And lithium is not one of the liquids or gases that I have listed here. So it's in the everybody else category. It's going to be a solid. Now to show you one that's a liquid, I decided to show you mercury. 273 is above 234 and below 630. So that's what tells me that mercury is going to be a liquid. So you can actually write this little SLG thing on your periodic or in your table S if that works for you, and use that, or you can memorize them, or you can do a combination of both. Doesn't matter to me. Two other terms you need to know are the terms monoatomic elements and diatomic elements. Your monoatomic elements, you're going to notice, are your noble gases. These are called monoatomic because they only exist as single atoms due to the fact that they don't bond with anybody. Our diatomics, again, those are our Hanaf-Klibrit, and those are the guys that we always see the little tiny 2s with. In terms of, like, do you need to blindly, like, memorize these? Maybe not quite so much, but you should, when you hear monoatomic, know that they're talking about somebody who's a single atom, likely a noble gas, and you should be able to, at this point, kind of identify what most of your diatomics are. You also need to know what something called allotropes are. An allotrope is two different forms of the same element that have different molecular arrangements and different properties. Now, interestingly enough, you're actually not required on the Regents to use the word allotrope, but you are expected to understand the concept of an allotrope. So I don't think the word's that hard. I think it's kind of easier to be able to say this word than always have to go through that whole definition. So I kind of like to give my chicken example here. Allotropes are the same thing, but they have different properties because they've been treated a different way somehow, okay? So if you were to go home and your mom were to say, hey, I'm going to make chicken tonight, she could make that chicken by baking that chicken. She could make that chicken by frying that chicken, okay? That chicken's going to taste a little bit different based on whether it's baked or fried, but it is still chicken, okay? So what I'm saying here, same ingredient, but a different arrangement of stuff or a different mode of preparation gives you different properties. So I want to first compare a really common example of the oxygen allotropes. O2 is gaseous oxygen, and the oxygen we breathe. And O3 is something called ozone. You're going to notice they bond a little bit differently. Oxygen actually bonds, O2 just bonds with like a regular double bond like this. O3 has this weird kind of sort of double bond. It's something called resonance. It's really weird. The molecules bend. It looks totally different. These two molecules are bonded differently. So they're both made of oxygen, but they're bonded differently. Because they're bonded differently, they behave differently. They have different properties, etc. So they're actually going to boil at different temperatures. You can actually smell ozone. That's kind of smell when it starts to rain. You can't really smell oxygen. Ozone can be used to kill pests in fields, actually. If you were to breathe only ozone, it's actually going to cause you problems. People who have asthma, if they breathe too much ozone on a humid day, have a problem because of this. Whereas oxygen, we actually need to survive. Your body can't deal with ozone the same way that it does with oxygen. There's a lot of carbon allotropes. Carbon can bond a lot of different ways. It's a very flexible bonder. You can have a diamond, which in diamond, carbon actually forms 4 bonds from each carbon atom to other carbon atoms and bonds in a 3D arrangement. So you'll notice on this picture there's bonds going, there's bonds going in this direction, there's bonds going into the page, coming out of the page, there's bonds going this way. So you're bonding on a lot of different dimensions. Graphite might be a little harder to see in this picture. Each of these carbons is only bonded to 3 other things, 3 other things generally. And what actually happens, this is actually one sheet of graphite, and then down here's another sheet of graphite. So these are 2 separate sheets. They have little kind of associations between them. They're not really bonds. So the difference between graphite and diamond, obviously they look a whole lot different. Something you know about a diamond is it's very hard. So because you have all those bonds going in different dimensions, going into different axes, you end up with a really hard compound or a really hard substance that has a very high melting point. Graphite is a lot softer. It's in pencils. You can write with it. If you push it on the page, it comes right off on your paper. Graphite also has some loosely held electrons that allow it to conduct a little bit of electricity. So those are some examples of carbon electrons. This is something called a buckyball. These are actually found in soot and kind of are the precursor to carbon nanotubes and some of that cool technology. So right now, carbon nanotubes are something that you might have heard about. This isn't stuff that you're going to get tested on, but just some kind of interesting things to sort of know. You can make really long structures that are very lightweight. They have great tensile strength. They can withstand a lot of pressure. And they actually are a semiconductor, so that can be a really helpful thing. They have very little friction when they're used together. They can be used actually in the medical field, possibly even. So this is a very cool kind of newer field in science. And that's actually where we're all good for today.